displaying query plans. So clustered index indications, ranges of value, group bys, order bys, sequentially accessed column, join columns. I love changing join columns to clustered indexes. Static columns, because if the clustered index changes and the row is caused to move, well, that means all the ancillary non-clustered indexes have to change. For the non-clustered, the documentation says that if you're going to be using more than about 20% of the table, the non-clustered index won't be used. Well, we already saw that those numbers are way disproportional. We saw a situation where if we use 1% of it, the table scan is faster than it is to bounce in and out of the index structure. I actually know the tech writer who got this from a systems engineer who I also know more than 20 years ago. And for some reason, that stayed in a lot of the documentation and stayed in a lot of the white papers. The number is closer to 5%, maybe closer to 1%, depending on what you're going after. The server does get smart about different ways of using the indexes. So, other limitations on the indices. Maximum of 16 columns for the index, maximum of 900 bytes of column width. Warning. Oh, I'm doing really good on time. I've hit 19 slides out of 60, and I've done 40 minutes out of 60. I'm going to have to talk a little bit faster. Warning. If you try to go over 16 columns, and by the way, I'm not advising a 16-column index. You want to keep these much narrower or feasible. You can go up to 16 columns. If you exceed 900 bytes in index width, you will get a warning, not an error. This, in my mind, is a mistake because it allows for sloppy design. But if you create an index on a column that's varchar 1000, the server will let you, it will simply warn you. What it's going to warn you about is, hey, you're going to try to insert a row and it's not going to work. This doesn't hit you until runtime, when a user actually types that much information in and the index that is on that column exceeds it. It kicks it back and the user calls you and says, hey, I'm getting this error here. I don't know what it means. What do you want me to do? This is my soapbox slide. The idea behind this slide is as follows. There are a lot of white papers out on the web that say all tables should have a unique primary key. Well, that's absolutely correct. Then they say for that primary key, you should cluster on it. That's not necessarily correct. Then they say you should have a narrow column. That is correct. Then they say it should be an integer. That is a good idea. Then they tell you to make an identity column. That may or may not be a good idea. I've seen many white papers that say every table should have a unique primary key, which is clustered, it is an identity column, and it is an integer. And I've seen lots of customer sites that follow that because it's a white paper and because that white paper has the word Microsoft on it someplace. That is typically a bad idea, and here's why. A primary key is a logical concept, not a physical concept. Indexes are physical concepts, not logical concepts. There is, however, a strong correlation between the two of them. Most design tools, when you go and change from a logical to a physical model, will try to make your primary key a clustered index. You need to keep in mind that a clustered index can be unique or non-unique. A primary key can be clustered or non-clustered. It's all a matter of which checkboxes you check or which syntax you use. Be aware that by making intelligent design decisions here at cluster versus non-cluster time, you can save yourself an enormous amount of performance pain. I'm going to be skipping through a lot of this for the interest of time. We have already talked about include columns. And now I'm going to jump into how the optimizer chooses the indexes. The optimizer is basically going to choose an index based on that first column. So if we're using the first column, we're going to go ahead and potentially use that index. As we start looking at these queries, let's take this from a design standpoint. And I'm not going to turn this back as a class exercise because I've been talking a lot and I'm running through time. But thinking about this one, select title from titles where the title is equal to stranger in a strange land. What are we going to index on? Well, we're going to index on title because that's what's in the where clause. If we're indexing on title, what type of index do we choose? Well, what we'll probably choose is a clustered if we have no other use for the clustered index. Otherwise, we'll choose a non-clustered. Non-clustered is a fine example or a fine use because you get index covering and we can pull the information right out of the leaf level of the index. However, every table should have a clustered index. Reason for that is otherwise everything gets stored as a heap at the tail end of the table, and 1,000 people all trying to insert into the same page is usually not a good idea. For the second query, select title from titles where the price is between $5 and $15. Now, if you're at a Barnes & Noble, chances are you've got an awful lot of books between $5 and $15. As a result, what we will probably do is create a clustered index on price. That way we can group all the books together. Or we will create a non-clustered on price include title. If we do not include title, we're probably going after too many rows for the index to be useful. The last one really rubs in an important topic, which is data distribution. In the first case, the price is between $5 and $15. That's a $10 range of values. But that $10 range of values probably encompasses half or more of the books in the bookstore. The next query says between $500 and $600. That is 10 times the range. But how many books at a Barnes & Noble are likely to be between $500 and $600? Probably none. At a rare bookstore you might find some, but not at a Barnes & Noble. So the range of data really has nothing to do with the number of rows that you're going to get, which has everything to do with whether or not you're going to choose an unclustered index. Important to be aware of because the optimizer does keep those statistics and it does use them. We've already talked about why going after too much of the data doesn't work mathematically. By the way, those of you who want a copy of this presentation afterwards, shoot me an email and ask for a copy of it. I'll send it to you. That way you can go through some of these in a lot more detail. Or sign up for a class. Bring this in and let us do this for all of your developers. It's a one-week class. And this section becomes a 2-hour presentation, not a 1-hour presentation. Oops. So, sorry I went past this when I warned you about the new clicking. It is feasible, occasionally likely, that a table scan is faster than the non-clustered index. This is based on calculations the server performs at optimization time. Now, what we've been looking at before is last name is Jeff and first name is, last name is Garbus and first name is Jeff. Now we have something a little bit different. We are priced between $5 and $10 or type is equal to computing. This is a bit different for the following reason. In order to resolve this query, I need to bring back all the books between $5 and $10. I also need to bring back all the computing books. This actually will require, usually, 2 passes of the data. One to bring back the ones priced appropriately, one to bring back of the right type. But here's the thing. What if we have a computer book that costs $9? We don't want that to come back twice. As a result, when we start looking at ORs, we have to take a number of things into account. First, do we have matching indexes for each of these sub-search arguments? Will a compound index help? What columns should be indexed? What will the optimizer pick? How do we avoid duplicates when we're bringing these things back? Let's take these one at a time. First, I will choose an index for each component of the search of the OR. So I'll bring back, use an index on that price. I'll use an index on the type. Note that in this situation, I would probably choose an index on price include type and another one on type include, on price include title and another one on type include title. Note that a combination of price type or type price really doesn't do anything at all for us. Which columns indexed? Just talk about them. Will a compound index help? No. If it says price and type, then your compound index is going to help. That's your telephone book lookup. We've already talked about the first example. The second example, you need to know that an in really is broken out into an or usually. It might be broken out into a table, but it usually gets broken out into an or. This will be first name equals Fred or first name equals Sally. And you can actually see that as you look at the optimization. So an index on first name is going to work just fine. At the top, how many indexes are going to be useful for the first query? 2, an index on last name and an index on first name. Down at the bottom, select from authors where the last name is in the list. Once again, the in becomes an or. There are 3 basic ways of resolving an or clause. The first way is with a table scan. A table scan says, read the whole table, filter the indexes out. Note that in this situation, and by the way, in more recent versions of the server, it no longer lists that filter step, although that's still happening, obviously. Most of the cost of the query is simply the table scan. Note that the table scan will happen if we do not have a matching index for a component of the or if all of the components of the or, all of the index accesses would add up to more than a table scan. That can happen as well sometimes. The next type of OR strategy is the multiple match index. The multiple match index occurs when we know that we can't get duplicate rows back. Bring me back all the rows where the key is in 1, 2, and 3. Well, I know if the key is 1, it can't be 2. If it's 2, it can't be 3. This allows me to run in parallel very smoothly, but also allows me to not have to avoid the duplicate. So what we're seeing here is this stream aggregate. The aggregate is the count, but we're using an index seek to bring all the data back.